Okay, hi everyone, and happy Monday and week 2 of quarantine. So let me know later if you found this video helpful. I was going to chop it up into small videos for each problem, but I think just for the ease of you finding everything in one place on Blackboard, I'm just going to leave it in one video. So I'll try to go through the problems a little bit quicker, which means if I'm going too fast, it's okay because it's a video. So you pause it and take notes, rewind, go back and, replay things. So don't forget that you can do that, and that's why I'm going to go a little bit faster so that the video is not going to be too long. So for Chapter 4, we are sticking with our schedule, and we're going to do some optimization problems. So what is an optimization problem? These are going to feel a little bit like related rates problems in that you're going to have to come up with equations yourself, and with these equations, most times you will have to solve, you'll have two different equations, and you'll be able to solve one equation for a variable and substitute that into the other equation to make things a little bit easier. So again, what does this mean? Like, what are some examples of what your optimization problems are going to be? Well, sometimes you'll be given a function to do things like minimizing costs. You might be maximizing profits, and again, they would usually give you a function. Now, to maximize an area or minimize some amount of material used, that's where you're going to have to write some functions or equations yourselves. So how can you write an equation relating two or more quantities? Just in the general sense, if we just think of some generic problem, basically. Maybe you're talking about the area of something. And if you're talking about the area of something, then we are going to want to relate the area of, I don't know, say a rectangle, to some other things. Well, area of a rectangle is length times width. But what we're saying is you're going to have enough information in the problem to think of area as either a function of the length or as a function of the width. So if that's the case, then we've rewritten the area as a function of just one variable, say just the width. Now, go back to your curve sketching techniques that you learned before. So how can you find an extreme value? How can you find a maximum or something? Well, you could find a maximum area where the derivative of your area function equals 0. You could see that would be where the area is at its highest, and then if you figure out what width gave you that highest area, then you're finding the width that causes the maximum area and hence the optimal value. So that's what everything is all about as far as optimization. As far as showing your number line, you want to, without graphing the area function or whatever we're talking about in each problem, without actually looking at a graph, you want to be able to say that, whatever value this is for W, over here my derivative of area was positive, over here it was negative. That must mean that I found something that causes a maximum area. So that's what I mean by show your number line for every problem, showing that you found the desired extreme. If you were looking for a max, you found a max. If you were looking for a min, you found a min. All right, so let's jump in with some examples. This is a chunk of problems out of your book. I would highly suggest, as usual, that you go back and try the odd problems on your own, and check those out in CalcChat, the solutions. So I'm going to pick a couple even problems to do. So right now I think I'm going to select number 4. Okay, so let's try number 4. What we're trying to do is find two positive numbers that satisfy the given requirements. So we want two numbers whose product is 185 and the sum is a minimum. So since you're trying to minimize the sum, this is what we're going to be looking for the minimum of. Okay, so this is what we're trying to optimize, is the sum, because we're trying to find the minimum of it. This is our extra piece of information that's going to help us to eliminate an extra variable that would make this problem not a Calc 1 problem anymore. All right, so the product of two numbers is 185. So let's call that P, and let's say that's 185. The sum of two numbers, we want it to be a minimum. Well, the two numbers, we have to decide on something to call them. So let's call them x, y. So going back to the product really quickly, the product of x and y would be written as xy. Now the sum of x and y is going to be x plus y. So we are going to want to find the derivative of the sum to figure out where it's at its minimum, where its optimal value is going to be. But right now there's too many variables. There's an x and a y. So in this equation, I need to look for x or y to get by itself. So then it doesn't matter. I'm going to choose to get the x by itself. So x is 185 divided by y. And now that I have that by itself, I can take that and plug it in for x over here. Alright, so then what do we have? We have s equals 185 over y plus y. We can take the derivative right now, but I would suggest first maybe making the derivative a little bit easier to find by rewriting the function. Okay, so now I'm going to continue on up here. So I have a nice function for s. Remember, this is what I want to optimize, so I'm going to take its derivative, which gives me s prime equals negative 185 y to the negative second plus 1. All right, now I have to find critical numbers here to put on a number line to find my maximum or minimum. So, and remember, this is from your curve sketching techniques. So I want to rewrite this again as negative 185 over y squared plus 1. And finally, try to make this look a little bit neater. If I get a common denominator of y squared, I end up with y squared minus 185. Alright, so how do we find critical numbers? Well, we're going to set the numerator equal to 0 and set the denominator equal to 0. When I set the numerator equal to 0, I get y equals plus or minus the square root of 185. When I set the denominator equal to 0, I get 0. Now keep in mind we wanted two positive numbers, so I'm only going to use the positive here. Alright, so we have an s prime, little place here to test out signs so that I could make sure I found what I wanted. Also, again, remember that we only want positive numbers, so I'm getting rid of things back here. So I'm going to put something from between 0 and 185. Let's try 1. If I plug a 1 into the derivative here, 1 squared minus 185 is negative, 1 squared is positive. So a negative over a positive is a negative. If I plug something that's on this side of 180, the square root of 185, say the square root of 200, right? Square root of 200 would be bigger. The square root of 200 squared is 200. 200 minus 185 is positive. The bottom's always positive. So this is going to be positive, which means our function decreased and then increased, which means this is the value for y that caused the sum to be a minimum. Okay? That caused the sum to be a minimum because the function decreased and then increased. So now we just have to answer the question. What are the two positive numbers? Well, the first one we found is that y is the square root of 185. So now we need what is x. Well, to find x, if you look around, you'll always find a place where x was kind of by itself. So let's see, let me get a different color here. Alright, so right here, if x was 185 over y, then we're going to say x is 185 over the square root of 185, which if you rationalize the denominator, this times this is 185, which cancels with that one. So we get also for x the square root of 185. So you might have been expecting two different numbers, and we could have gotten two different numbers, but we didn't. We got the same number. Okay, so that's one problem. All right, let's try one more. All right, so we are going to now look at number 8. The sum of the first number squared, and the second number is 54, and the product is a maximum. All right, the product is a maximum. This time, let me start out by writing the product of two numbers. Okay, so this is what we're going to eventually want to find the derivative of, because that's what we're trying to find the maximum for. Okay, so that's our equation that's being optimized. So what's our extra information that we can use to get rid of either the x or the y? It's that the sum of the first number squared and the second number is 54. Just write that out as a mathematical equation exactly the way you just read it. So the sum of the first number squared and the second number is 54. All right, so now we have to solve for either x or y. Now I told you in the last one it didn't matter which variable you solve for, and it still doesn't, but there's definitely a more natural choice here. Would you rather solve for x squared or y? Yes. Okay. I'm just hearing you all say y. All right, so y is 54 minus x squared. So we're going to take this and plug it in for y in the product equation. So the product is x times 54 minus x squared. And before we take a derivative, why don't we make that look a little bit nicer so we're not stuck using a product rule. Okay, there we go. So this is the equation for the product, and now we need to maximize it. So if we need to maximize it, let's start using our curve sketching techniques, which means we want to find p prime. So p prime is what? Try this yourself first. All right. Now we need our critical numbers. So now we're going to set this thing equal to 0. And then let's divide both sides by 3. Okay. Now, I would normally say x is plus or minus the square root of 18, or plus or minus 3 times the square root of 2. We are really just going to be using the positive 3 times the square root of 2 right now. Because, again, we want two positive numbers. All right, so let's do our number line. But on here, and I think you'll see why, the math will be a little easier if I think of that as the square root of 18. So I need to plug something from this interval up into the derivative. So if I take a 0 and plug it in, I get 54 minus 0. So 54 minus 0 is going to be positive. Now if I plug something from here into the derivative, say the square root of 25, because the square root of 25 would be larger than this. Well, the square root of 25 is just 5. So 54 minus 3 times 5 squared, that's 75. So 54 minus 75 will be negative. That means that my function increased and then decreased, my product function, which means that this causes, this is the x value that causes a maximum product. All right, so what will your answer be? Well, we have x equals 3 times the square root of 2, and then we just need our y. Now, y, if you notice back here, Sorry, I'm just trying to get something that's, you guys can't see it, but there's a little thing at the bottom here in my way, and I can't write towards the bottom. So if I'm looking, say, right here, then I get y equals 54 minus x squared. If I think of x right now as the square root of 18, squaring the square root of 18 gives you 18, and 54 minus 18 gives you 36. Okay. So those are your two numbers, where if you take the sum of the first number squared and then the second number, you get a product that is the maximum product. All right. Last page. Okay, so now we have an application problem where we're going to have to, we want to probably draw a picture here. So we have a rectangular solid with a square base. So let's draw a box that has a square base. So this length and this length would be the same, but we don't know how high it is, so I'll just call that h. Has a surface area of 337.5 square meters. All right, so the surface area is the area of all of the surfaces. So I have a front and a back whose area is x by h, and then I have two sides whose areas are x and h. So that's the front, the back, the right side, the left side. So that's four areas, four surfaces who have areas of x, h. And then I also have a top, which is x by x. And then I have the same thing on the bottom, x by x. So I have two sides whose area is x squared. Also, they tell you that your surface area is 337.5 square centimeters. Okay, so that's going to be, I don't think I've used the term before, but that'll be your secondary equation. Your primary equation comes from what you're trying to maximize, and we're trying to maximize the volume, which is the length times the width times the height. Okay, so you can see again we have too many variables. To get rid of one of the variables, we are going to look for the best variable to eliminate up here, to get by itself up here. You have this h, and here you have an x squared and an x. So the x, I believe, you should see that that's going to be definitely harder to solve for. So let's get the h by itself. I'm not going to show all the steps to try to make this already long video a little bit shorter. So what would we have? We would have h is 337.5 minus 2x squared, and then that would be all divided by 4x. Alright, so this is going to be plugged in for h before we find our derivative. So your volume is x squared times what we just got for h. And as we've been doing, you want to simplify this a little bit before you move on. So we can cancel that x with that x. And I can also now write my volume equation as 1/4, so I'm not looking at this as a fraction. And I'm going to distribute this x through that quantity. So then I would have 337.5x minus 2x cubed. Alright, so let's now take our derivative. Alright, so then we have v prime is, we just have a coefficient now just sort of hanging out, and then this derivative is nice and easy to take. Alright, so what do we do with the derivative? We use it to find critical numbers. If we set 1/4 equal to 0, that doesn't really give us anything. If we set this part equal to 0, we get 337.5 is 6x squared, so then x squared equals, and you can grab your calculator if you're trying this on your own, 56.25, so then x equals plus or minus 7.5. But again, these are dimensions for an actual shape, so a negative isn't going to make any sense. So when I'm checking my signs for my derivative of volume, I'm only going to put the positive 7.5 on here. If I plug a 0 in here, to my derivative, I get 337.5 minus 0, so that's going to be positive. And if I plug in a, let's say a 10, that would give me 10 squared is 100, so 337.5 minus 600 would give me a negative. So that means that my function increased then decreased, so this did indeed produce a maximum. So we just have to answer the question now, which is what are the dimensions? So you can say x is 7.5 centimeters and y equals, not y, let me make the match what I did before, that would be an h. So h equals, or you can label it right on your picture. So this would be 7.5 centimeters, this would be 7.5 centimeters, and then we again are still looking for h. So where can we find h? Right here. So h is going to be 337.5 minus 2 times x squared all over 4 times x. And I know I squished that in there, but I'm having a problem with not being able to use the bottom of this page to write on. So if you calculate that, just again grab your calculator, you get 9.375, that looks like a comma, 9.375 centimeters. And those are our dimensions, or again you can put it on the picture. So this isn't really to scale now, you can see, because the height would be the biggest. So hopefully these problems helped. You would also, I would highly suggest you visit Hippocampus. That's always my favorite one to recommend first, because they're very neat and organized with their steps. It should be in the Calculus 1 course at the bottom, but it might be at the beginning of the Calc 2. Pretty sure it's in the 1. And then, of course, you can always Google Khan, or for YouTube, my suggestion is usually to go to the channel Patrick JMT. All right, I will make sure that the WebAssign due dates and assignments are correct. I might throw in one of those extra quiz assignments. And if you have any questions, click on Ask Your Instructor in WebAssign or send me an email. All right, have a great day.